Hello and welcome. Today we're going to dive into this incredible story that connects an ancient Greek idea with the future of medicine. You're going to see how understanding the tiniest thing in the universe, the atom, is actually helping us solve one of our biggest problems, detecting diseases early. So let's put on our detective hats and follow the clues. We're going to start with a question that sounds like it's straight out of science fiction.
I mean, it sounds impossible, right? But what if it isn't? Scientists right now are working on a future where a simple, totally painless breath test could reveal the earliest signs of really serious illnesses, like lung cancer. The key to this whole thing is hidden in the tiny molecules we exhale every second. So, how on earth can our breath hold such important secrets? Well, it all comes down to the hunt for something scientists call molecular fingerprints.
And that fingerprint has a scientific name, a biomarker. You should think of it like a clue. It's a very specific molecule that, when it shows up in something as simple as your breath, can tell doctors that something's wrong, way before other symptoms might ever appear.
Here's the problem. Diseases like lung cancer are notoriously hard to catch early. The methods we have now can be invasive, or sometimes they're just not reliable enough. So the goal is to create a test that can identify these biomarker molecules accurately and simply. But to identify a specific molecule, you have to understand what a molecule is at its most basic level, what gives it its unique identity. And to answer that, we can't just look at modern medicine. We have to rewind the clock way, way back to the very first time someone asked, "Hey, what is all this stuff made of?"
So our investigation is going to start over 2,000 years ago, in ancient Greece. Long before we had microscopes or labs, the first clues about matter didn't come from experiments, but from a really powerful thought exercise.
The ancient Greeks were the first to come up with this pretty radical idea, that if you just keep cutting something in half over and over, you'll eventually hit a tiny, indivisible particle. They called it atomos, which literally means uncuttable. It was a brilliant philosophical concept, but it stayed just that, an idea, for 2 millennia, just waiting for the tools of science to catch up and test it.
Okay, fast forward to the early 1800s. A man named John Dalton takes that ancient idea and, through actual observation and experiment, turns it into a scientific theory. This is the moment the idea becomes real science. Dalton's huge insight was that each element, like oxygen or gold, is made of its own unique kind of atom. And crucially, these atoms combine in fixed, predictable ways. For the very first time, we had a scientific rule book for how stuff works.
But what even was an atom? Dalton pictured it as a solid, indivisible ball. The truth, as scientists were about to find out, was way stranger and a lot more interesting. The next 100 years became this thrilling detective story to see what was actually inside.
This timeline just shows you the rapid-fire discoveries that completely shattered the old model. First, boom, 1897, J.J. Thomson finds the electron. And suddenly, the uncuttable atom has parts. Then the really big shocker, in 1911, Ernest Rutherford discovers the atom is mostly empty space, with this tiny, dense, positive nucleus at its core. And finally, in 1932, James Chadwick finds the last piece of the puzzle, the neutral neutron, hiding out in the nucleus. In less than 40 years, our entire picture of matter was redrawn.
With all those discoveries, we finally had the blueprints for the modern atom, the fundamental building block of, well, literally everything.
So, let's meet our cast of characters. In the center, in the nucleus, you've got the heavyweights, the positive protons and the neutral neutrons. They're packed in there tight, and they give the atom almost all of its mass. Then on the outside, you've got these tiny, lightweight, negative electrons just zipping around that core. It's this perfect balance of positive and negative charges that makes a normal atom electrically neutral.
And this just brilliantly illustrates that point about empty space. To put this number in perspective for you, if the nucleus were the size of a marble sitting on the 50-yard line of a football field, the atom itself would be the size of the entire stadium. That's just mind-blowing. Matter is mostly nothing.
So, if all atoms are made of the same 3 particles, what makes carbon different from oxygen? The answer is simple, and it's the single most important rule in all of chemistry, the atomic number. It's just the number of protons, and that number acts as the atom's unchangeable ID badge. If an atom has 6 protons, it's carbon, always. If it has 8, it's oxygen. No exceptions, ever.
The mass number is even simpler. It's just the total count of the heavy particles in the nucleus. You just add the protons and the neutrons together. So if a carbon atom has 6 protons and 6 neutrons, its mass number is 12. This just tells you the approximate weight of that specific atom.
Now here's where it gets interesting. You can have atoms with the same number of protons, so they're the same element, but they have a different number of neutrons. These are called isotopes. Think of them as just different versions of the same element. For example, all carbon atoms have 6 protons, but some might have 6 neutrons, while others could have 7 or even 8. Same identity, just a slightly different weight.
Okay, so we've cracked the code of the atom. Now let's connect all of this fundamental science all the way back to our opening question about that diagnostic breath test.
And here's how it all connects. It's really this simple. Just as the proton count defines an atom, the specific recipe of atoms defines a molecule. 2 hydrogen atoms and 1 oxygen atom will always form water. If you change that recipe by even 1 single atom, you have a completely different substance.
And this slide brings it all home. Let's just walk through the logic together, step by step. 1. We know an atom's identity comes from its protons. 2. We know these unique atoms bond together in fixed ways to make unique molecules. 3. That molecular recipe, its chemical formula, is its unique fingerprint. 4. The diseases we're trying to detect release specific molecules, those biomarkers, into our bodies. And 5. That futuristic breath test? It's simply a highly advanced detector that's designed to spot those exact molecular fingerprints. It's a straight line, from the proton to the diagnosis.
So it all comes back to this. By understanding the fundamental rules that govern the absolute smallest particles of matter, we are unlocking the ability to read the most subtle signals our own bodies send out. The journey from a philosopher's thought experiment all the way to a life-saving diagnostic tool shows us that sometimes the biggest answers can be found in the smallest of places. The question now is, what other secrets are just waiting to be uncovered?